what comes out here. Now, there is one more important feature in the case of the transformer that we need to be careful about while designing is the volt second balance. The volt second balance, this actually comes from the Faraday's law of electromagnetism. And what does Faraday's law of electromagnetism state? It says that the induced voltage E is equal to N, the number of turns in the core, d phi by dt into d phi by dt, where phi is the flux in the core. That is, if we have a core of N turns winding on the core, and then if we apply a voltage E, there is going to be a flux set up due to the fact that there is a current flowing, and the rate of change of flux into N is going to induce the same voltage E here. Now, this voltage E, which is equal to N d phi by dt, or N AC dB by dt, where phi is equal to B into A, because flux density B is flux by the area of cross section of the core. So, N AC dB by dt, and therefore, the flux is given by 1 by N AC integral of E dt. Now, N and AC are constants, and therefore, B is proportional to integral of E dt. This is the volts and this is the second. That is what is known as the volt second balance, meaning this integrand on integration should not have a waveform that is continually increasing, meaning E should not be a DC value. If E is a DC constant value, on integrating, this would be the constant into T. So, which means it is a continuously increasing value, and after some time the flux density for the particular core, for every core or every type of core material, there is a value of flux density beyond which the flux density will not increase. That is when we say the core is saturated and it loses its electromagnetic property. So, if this value here, integral of E dt, is continuously increasing, then a time approaches when the value goes beyond the flux density permitted for the core, and the core will saturate, it loses its electromagnetic property, and it will just be a plain short circuit. Therefore, it is essential that for that particular core, this volt second integral of E dt is nothing but the area under the voltage curve. The area under the voltage curve should not go beyond a value whatever is permissible for that core, whatever the flux density permissible for the core. This is the volt second balance. If, for example, we have E is a constant, constant of amplitude V, then integral of V dt is going to be V into T, and this has a ramp waveform, and this keeps on increasing beyond a particular value where we have B sat. Beyond that particular value, the flux core will saturate and it loses its magnetic properties. If E were sinusoidal, Vm sine omega t, then this would result in Vm cos omega t by omega as the this one, and it is divided by omega 2 pi f, and therefore this value has a sinusoidal character, but the peak values are always Vm by omega, and the design value of Vm by omega should be such that this does not exceed V sat of the core. In such a case, the core will not saturate and it will retain its magnetic properties. This is the volt second balance which one need to be conscious about while designing. Now, for sinusoidal waveforms, again from the Faraday's law of electromagnetism, we have E which is equal to N AC dB by dt. Let us draw the BH curve. We have H and B. Let us draw the approximate BH curve. This is the BH curve. Now, you should see that beyond this particular value of flux, this we call it as B sat. Beyond that value of flux, the core saturates. Beyond this value of flux density minus B sat, the core saturates. So, you have to operate at a slightly safer value. Let us say that we do not allow for saturation and that the flux is allowed to swing only between some plus Bm to minus Bm, which is less than V sat. So, then the whole swing of the BH loop is like that. So, that will be the BH loop that will be traversed if the flux within the core were Bm, that is, it swings from minus Bm to plus Bm to minus Bm, so on. Now, going from minus Bm to plus Bm takes half a cycle, and again from plus Bm to minus Bm takes another half a cycle. So, one full cycle means minus Bm to plus Bm to minus Bm is one full cycle. So, let us take any one of the half cycle, which is the flux density swinging from minus Bm to plus Bm or plus Bm to minus Bm in a time span of t by 2. So, we have integral E dt which is equal to N AC B. NAC B, and the B has swung from minus Bm to plus Bm, that is a total swing of 2 Bm in that time, in the time of 0 to t by 2. So, let me multiply throughout by 1 by t by 2 and here also 1 by t by 2. So, this portion is nothing but the average voltage E average across the coil, and this is 2 by T N AC, and the flux that is swung from from minus Bm to plus Bm is 2 Bm in a span of T by 2, which is 2 Bm. So 1 by T is nothing but the frequency. So we use 2 N AC, this 2 and 2 becomes 4 N AC frequency into Bm. This is E average. We would like to express everything in terms of the effective value or the RMS value. In sinusoidal analysis. Therefore, we use the relationship that we obtained few classes ago when dealing with sinusoidal waveform. The RMS value divided by the average value is 1.11, and therefore RMS value is equal to 1.11 into average value. So using that relationship here, if we need to have the RMS value, that will be equal to 1.11 average value, which is equal to 1.11 into 4 N AC F Bm, or we have the voltage across the coil E RMS, which is equal to 4.44 N AC F Bm. This is a pretty important voltage equation for the transformer or the voltage across a coil when we are talking of sinusoids. Now looking at this equation, the voltage E, if we don't put any subscript here as RMS or average or peak, if a subscript is not used, then it automatically means the effective value or the RMS value is given by 4.44 N AC F Bm. Now looking at this equation, we see that the voltage that is induced is proportional to the number of turns, and there is the frequency dependence which comes in the frequency of the applied voltage, and this is the maximum allowable flux density. Flux density max allowed. Note here, for various materials, I can give the approximate figures. For ferrite materials, B sat is around 0.3 Tesla. So Bm should be less than 0.3 Tesla, should be around 0.25 Tesla. For CRGO, this means cold rolled grain oriented silicon steel. B sat is around 1.2 Tesla, and normally Bm is chosen around 1 Tesla, so that it is less than the B sat value and still retains the magnetic properties. For cold rolled non grain oriented CRNGO, cold rolled non-grain oriented silicon steel. For this, BSAT is around 1 Tesla and BM is normally chosen around 0.8 to 0.9 Tesla. So, like that, for different materials, different BSAT, they are the inherent property of the magnetic material. Different BSATs are available and the operating flux swings, the flux density swing should be less than the BSAT value. So, that is the value that has to be used for used in the design equation there. Now, look at a slightly different formation of the equation with this and this brought together on one side. In that case, we have E by F, which is equal to 4.44 N AC BM. So, for a core, for a transformer design, this is a constant, and once a core is chosen, this is a constant, and once the core is chosen and the number of turns are fixed, the flux density in the core, the maximum operating flux density in the core is also fixed. Then which means this figure is a constant. This voltage by F, V by F, E by F being a constant also means or implies that volt second is a constant. So, one has to design for a volt second product in the case of the transformer such that the flux in the core does not exceed, the maximum flux density in the core BM does not exceed BSAT for that core. That is the important conclusion that you should draw from this particular